Hello, I'm Ed Wicklein with Perello Engineers, and I'm here today to talk about the Technical Guidance Manual, Computational Fluid Dynamic Modeling of Chlorine Contact Basins that I've helped the Colorado Department of Public Health and Environment develop. We've recorded some modules in support of this guidance document. Today, we're going to go through the guidance document, its organization, its rationale. This is Module 2. So, the organization and rationale. CDPHE has developed a document summarizing best practices and standards for CFD modeling of chlorine contact basins. The goal was to standardize how modeling is being done. This helps facilitate review for the agency, and it provides background for both the modeler and the reviewer on best practices. The key terms we're going to be using quite a bit today: computational fluid dynamics, or CFD, a CCB, it's a chlorine contact basin, hydraulic residence time, which is the volume of the basin divided by its flow rate, and the baffle factor, which is the hydraulic efficiency of the basin. The guidance document's organized into 6 chapters with an executive summary at the beginning, 6 chapters walking through the process, and then a number of appendices that help support production of high quality CFD models and results that are easy for the district to interpret. So in the introduction section, we'll talk a little bit about chlorine disinfection, the baffle factor concept, which is the time it takes a tracer, it takes 10% of a tracer to travel through a basin. There's some uncertainty with the baffle factor. US EPA's got a table that they publish with 5 levels of baffling and the T10 for those, with some description, but it can be hard to look at geometry and know ahead of time exactly where it's going to fall on this. There's certainly uncertainty in very non-standard designs that are sometimes used, and then some discussion on baffle factor measurement and limitations. Section 2 discusses some background on CFD modeling of CCBs, modeling approach. So the typical approach with the CFD model is known as the frozen fluid. The model's built, the velocity field is solved. We assume that for a given flow rate and water level that there's an average solution to the basin. And this was developed when we had slightly less computer power, but it's still advantageous today. And then following this, the flow field is held frozen, and the tracer is simulated and transported through this field. From this, we can generate an RTD curve and determine our T10. And then there's some discussion on modeling standards, how much geometry should be included, the operating flows and depths that the state would like to see, fluid properties that should be used, and an estimated level of effort for this type of work. Section 3 gets into more details on the modeling process. We've got this flow chart with a number of loops that occur in the middle. This ensures that we get a good quality model. We discuss software, model development, more on geometry, computational mesh, and simulation process. So for software, well-validated software must be used. One can write their own CFD code, but it doesn't go through a very rigorous validation process. So we like codes to be used that have been well validated by a number of different users in different industries, so all of the bugs and problems are worked out. We want codes that have been extensively referenced in peer-reviewed literature for CCB modeling so that we know that they're accurate and valid for these types of problems. So there are commercial and open source products available. Common commercial packages would be Fluid or CFX developed by ANSYS, Star CCM Plus developed by Siemens, Flow 3D, or OpenFOAM, which is an open source software that's been developed jointly by people around the world. And it's been shown to be fairly accurate, and there are a number of CCB examples in the literature using this software. For the model geometry, it needs to be 3D in some sort of electronic format. It could come from a 3D CAD file, could be generated by the modeler or a CAD individual from 2D drawings or printed sheets. Field measurements could contribute to this. Sometimes things are made after it's built, and so verification can sometimes be helpful, although it's not always possible. And once we have a geometry, a computational mesh is developed within the geometry where the flow field is going to be solved. Typically, the mesh is unstructured. There's a number of cell types that can be used, that the solution equations are then broken down to and solved on, ranging from 4 faced tetrahedral elements made up of 4 triangles to hexahedrals, which are 6 faced elements. Those 2 are probably the most common. Transitioning between them, wedges and pyramids are used. And then a number of codes are now using polyhedral elements that are a conglomeration of tetrahedrals, essentially. And the idea is that we want our flow entering and exiting the computational cell normal to the face to get the highest quality solution. And so some of these elements can lend themselves more to that than others, depending on the geometry they're representing. The actual cell size typically ranges from 1 inch to 12 inches within the problems we're solving. Sometimes it can be a little bit larger. Sometimes it needs to be a little bit smaller, depending on the feature we're trying to represent. The mesh quality is very important. If you have a poor quality mesh, you're going to get a poor solution. The model will sometimes give you a nice colorful picture, but it might not be accurate. Skewness is a key parameter for all solvers. It's a measure of how far the cell face deviates from equilateral. So ideally, everything would be perfectly balanced, but you can work out a range. And generally, it should be less than 0.9. Occasionally, cells higher than that can be tolerated. It's a little bit sensitive to the solver itself. Orthogonality is also important. It's a measurement of the vector angle between cells as you move from one to the next. The cell length ratio is also important. Ideally, the cells equal on all sides, but that could lead to a large mesh, or you could be trying to represent a geometry where that's difficult. And so they can be stretched somewhat. Every solver has its own specific requirements, but there's general guidelines, which we discuss in the document. And then smoothness, when we're using unstructured meshes, or even a structured mesh, there can be a rate of change between adjacent cells. And you don't want too large a difference, and so we'd like a smooth transition between these sizes. Mesh independence is another parameter that's important, particularly for disinfection problems where human health is our primary goal. So we require a mesh independent study to be conducted as part of chlorine contact basin modeling for approval by CDPHE. And so a mesh resolution study establishes that the solution is independent of the mesh size. Obviously, if we only have 2 cells across a channel, we can't really resolve what's going on in the flow field. But do we need 100 cells to represent it? Probably not. So a mesh independent study is done for each problem to determine the required resolution that we have. Typically, point values are compared at some location of interest, and we're looking for an R squared of 0.95 or better between the 2 meshes. So in this example on the right, our initial mesh to our fine mesh, we've increased our cell count by 31% approximately. We've improved the resolution, but the difference between the 2 solutions still has some variability. When we further refine it between the medium and the fine and compare the same locations, we find that the R squared is 0.98, so the solution hasn't changed very much going from this medium to fine condition, and therefore we would conclude that the medium mesh is sufficiently refined for our problem. Now we also have the simulation setup. There's a little bit of a loop here between the simulation setup and the mesh independence. You would do an initial setup, run the mesh independence. Once that's done, we set up all of the problems we actually want to solve. We need to set our fluid properties. Site properties could be used if they're known, or we'll default to 4 Celsius as a cold water approximate condition. Turbulence models, there's a number of turbulence models available. At a minimum, a 2-equation RANS type model, K epsilon or better, needs to be used. And the solver needs to be second order accurate or higher. On the right is the fluid setup screen. You can see that moving down the left side or across the top are the same things, and these are all of the steps one would walk through to set up a given problem. We'll go through this on a subsequent model. The geometry and model boundary conditions need to be set appropriately. Of course, an accurate geometry is required to get a good solution. And the boundaries need to be a sufficient distance from the area of interest. The example on the right shows having 2.5 diameters of pipe versus 10 diameters of pipe approaching this elbow. We can see that there's areas where the flow field deviates quite a bit between the two. And so we just need to make sure that we have a sufficient amount of approach condition upstream. Appropriate types of boundaries would be some type of inflow, either velocity or mass flow rate, an outflow, either a set fraction of flow or a pressure outlet, and wall boundaries, which would be a rigid surface that flow can't travel through. And for the hydraulic solution and convergence, there's a number of things that need to be monitored. The baseline, you monitor the residual, the difference between your solution for progressive iterations as the model solves the Navier-Stokes equations, then checks against the prior solution. So this is monitored, and ideally we like to see 0.001 or less for the global average residual. Some problems are a little bit unstable and don't quite reach that, but we would like to see that if at all possible, and if not, there should be some discussion on why that can't be reached. There's also parameters of interest that should be monitored to establish whether or not the solutions converge. So you can monitor data at specific points within the domain where things might be going on, or monitor conditions out plane. You might be interested in the velocity, pressure, mass flow through an area, turbulence, or other metrics. So the image on the lower right would show point velocity monitoring. You can see that the white line is at a place where it's very stable for many, many, many iterations. But the red line is tracking a point where there's some sort of instability in the flow. Looking at it, if you took an average, it's certainly fluctuating about a known point. And it appears that for the initial set of iterations, there is some variability, but then it stabilizes. And so we would conclude that it's probably a converged solution. We'd like to stop it at perhaps an average point, but this will all be included in the report. Following simulation of the hydraulics, the tracer simulation is done. There's a number of ways this can be done, either Eulerian, simulating a step dose test, which is probably the most common now, or a slug dose test, which can also be done. It's a little bit less common. With a step dose test, it's fairly easy. You just change the influent to a conservative tracer with the same properties as water, and it's tracked through the system. The slug dose, you need to feed it for a period of time and then stop the feed and track it as it travels through. So the feed should be less than 2% of the hydraulic residence time in this case. The reason a step dose test would be preferred is as the slug dose gets diffused through the domain, we start getting into very small numbers, and there can be some round off error in the solution. You can also use a Lagrangian method with particle tracking, releasing particles at the inlet and tracking them through the domain. This approach is also appropriate. It tends to predict a slightly lower baffle factor, and so it is conservative. In both cases, you really need to consider the turbulent transport of the particles or the tracer. So with the Eulerian model, you need to set a diffusivity coefficient. It's not overly sensitive to that. There's an equation given in the guidance manual, but some variability exists in it due to the turbulent Schmidt number that's part of the equation. For contact basin modeling, there's some recommendations in the literature for what should be used for that value. With Lagrangian particle tracking, we need a discrete random walk model, which tries to incorporate the turbulent fluctuations into the particle paths. It's not a perfect approach, and this is probably where some of the differences come in the baffle factor between the two methods. The particles tend to follow the bulk flow, and so may travel through the domain quicker than all of the flow would otherwise get there, leading to this lower baffle factor. Following the simulation, there's post-processing of results. You generate figures that show what's going on. Here we've got on the left side would be the velocity field in a tank. And then we release the tracer, which is time process, and we can see the tracer traveling through our domain. We're recording the tracer at the outlet. And we generate the curve we see on the right side. The tracer being monitored, in this case it was a slug dose test, and we see the peak. We convert it to the total tracer through the system. And from this we can figure out our T10, the time it takes 10% of the tracer to reach the outlet, giving us the baffle factor. In this case, 0.52 for this serpentine path. Following post-processing of results, the whole study needs to be documented, and qualifications minimum level is Colorado professional engineer should be conducting the study. And then in the reporting, there's a standardized report template in the appendix as an example, but we want to have basic project information discussion, details on model geometry and mesh, the CFD model setup and summary, all key figures that are required to explain and understand what's going on, and any supplemental or other pertinent information the reviewer might want. So the appendices, the Appendix A is a model review checklist that the CDPHE reviewer would go through when reviewing the report to make sure that all key information is in there. The person who prepares the report can fill out the details to facilitate the review and make sure that nothing was missed. And then that makes it easy for CDPHE to review it. There's a number of steps of different things that need to be looked for and documented. Appendix B is a sample report, including the filled out Appendix A to go with it, showing how the report could be set up and what types of figures might want to be included. Appendix C is an example library of CFD models, the CCBs. The preliminary ones that are available are in there, and this is expected to grow as more reports are submitted using CFD modeling. This will help reviewers also evaluate quality of model and start to understand how different features help affect the baffle factor. And finally, Appendix D is just a review of the key literature done to date on CCB modeling with CFD models. And with that, you can always email me questions if you have them, or we will have the Q&A session after these modules have been reviewed the initial time, and that should hopefully also be recorded with those questions answered and included in the legacy documents. With that, thank you.